So
Yeah.
since you can be a little bit late.
All right. So we got our CDR here. I mean, I just have the goals, right? And then I have like sub-team goals here, but the way I've done my requirements is I'm just going straight from the actual team goals. These are just like what I want to focus on controls. Yeah. So, uh, and then like so, most of the specifications are largely the same from last time. It's just consolidated. So this one is exactly the same, right? This is just defining the controller, what I think that definition should be. And then next one is just life cycle, right? There are many things that just corner cases that you want to consider, and so I just stipulated all the different things that we're going to do to basically consider the life cycle of control systems. So, I mean, number one, of course, is FMEA, and then there's a couple of smaller ones that are variously found in the vehicle specifications. And then the other part, life cycle between using, then there's actually uh, from a mechanical standpoint, assembly, disassembly, maintenance, and then yeah, I have a bunch of things here. I've added like from a code perspective as well. I want easy modifying, debugging, and tuning, because otherwise it might take too long to do control stuff. And yeah, the last requirement is just rules. And I remember now that these are not all the rules, but later on I will have the complete rules that are relevant to me. So the first one, what I've done here is gone through all the different specifications, and then I've analyzed each system and said, well, here are all the specifications. Which ones apply to this system, and how do I fulfill them? So yeah, just going down here. The first one is the location of the navigation enclosure. So it's best if it's at the center of gravity for the accuracy of the accelerometer. But if it can't be at the center of gravity, the one axis that is like the easiest to move along is the z-axis. If Because the yaw rate is the largest angular velocity of all of the three components. So we're going to end up moving it a little higher for the purposes of uh, being able to remove it without removing the battery. And then this next one is an idea about a mechanical filter. I can't justify this requirement. That's why I have it in red. Right now, the idea is to just, like, as it says, to test different materials to see if I can get an improvement compared to none. And then this next one is fairly important. So on per 23, the rear wing was covering the GPS antenna a little bit, and anything obstructing the antenna is going to be not helpful. So I do want to move the antenna higher up than where it was before, so to minimize obstruction from the arrow. And so, and this other one, this fourth one here is talking about EMI. So if we are going to do a metal enclosure, I would like it to be made out of something ferrous. The reason why I didn't want to do this before is because magnetometer will be completely useless if it's enclosed in a EMI blocking container. But I think it is more important to have accurate gyro and IMU, or just IMU in general, than it is to have that additional information from the magnetometer. Yes?
So, like, just to clarify, VCU, when you say VCU, you're talking about torque vectoring and not main?
No. I'm talking about torque vectoring.
Okay. Just wanted to clarify.
And then with grounding, having a metal enclosure will automatically solve this problem. But if we don't have a metal enclosure, we'll have to do like some sort of weird wires to ground all the hardware to probably the firewall. So that's something to consider.
Instead of a ferrous enclosure, there are a couple other options.
Yeah, like aluminum wouldn't be bad, but
yeah, but like you can just buy like an EMI enclosure. Like that's a thing, you can just buy these.
what's their working principle?
Faraday cage.
A what?
It's metal.
Yeah, it is metal, but like
Oh,
it would have like some rating for TMI. So if you have a
Uh,
target for that, you could shop for an enclosure
if
that
I
has
have a
TMIs.
target, I see. Yeah, I mean,
I think a metal box is a good Faraday cage.
yeah, that's the idea. Any metal is just something that is iron is best. That's all.
Something I've also seen is that like if you had an aluminum closure, you could line it with copper foil, like the foil tape we use on
Mhm.
suspension.
I thought aluminum was fine.
Yeah,
But
aluminum
if
is
were it not fine, that could be like
Yes.
an improvement you could make.
So from what I'm hearing, you're officially no longer going to use the magnetometer.
Yeah, I don't think that's the most. Yeah, I don't think that's going to improve our estimates.
Also, GPS antenna located in the clear line of sight of the sky is going to be near impossible to meet. Like just based on roll hoop, firewall, head padding, and wing. Like
We can find
It's
it.
pretty much good how it is. It's just that
wait, when you say is this
GPS
the
antenna
the
connects to the the GPS antenna connects to nav, then it routes. So if you've seen on the cards a
Is
little
this the-
black box on,
so it's
It's
not
like-
like in the book?
It's
no,
Okay.
it's attached. It's just that the wing is like here, and then the antenna is here. So it's if you just move it like that, that would make
So this is the
Nice.
one with like the round base and the
so
wire.
it's located.
yeah. I mean, I'll have a diagram showing what I'm talking
It's
about.
located almost exactly where the DAC antenna is right now.
Yeah.
It's like right next to that.
Okay.
So this one, this doesn't have a lot of important specifications. Like for waterproofing, I'm just gonna have a lid and a polycarbonate lid and just have a gasket between. I think that will be sufficient. It doesn't have to be super tight, watertight. So yeah, I mean, I'll just skip down to like this flimsy construction. I think this one's already fine as it is, but I'm just gonna do basically the same thing where the bobbins, which is like the damping sandwich part, is just permanently attached to the car, and then all you do is unscrew some nuts to get the enclosure off. I like that design, and it was very sturdy. And then, yeah, again, there's this. I mean, eventually we'll have to make the decision on what kind of enclosure we're gonna do. But yeah, I have stiffness requirements. 2 millimeters was used for like driveline on 22, and that clearly was too weak. So it has to be thicker than that.
So those USB clamps we're talking about, is that like the double-ended female clamp
Yeah.
where it's like sitting in the wall?
Yeah. I think some sort of snap fit is probably doable. Just 3D print it. I think this is the last set of requirements. So the big one here is I'll use like wing nuts instead of regular nuts so that you can just take off nav without tools, and you can torque it down sufficiently that it probably won't unscrew. And but in addition, like there's just a lot of these requirements that are making it as easy as possible to work with this enclosure. And the big one here is I do want to be able to wirelessly update the code so that I don't have to take off the enclosure and I don't have to remove the lid, because I mean the lid has to be there for waterproofing reasons, right? So it makes the whole thing inconvenient if I have to flash the code by directly connecting into the enclosure.
Do the wing nuts have any kind of like locking, like is it nylock or patch lock?
I don't think so. It's just normal,
Can you get ones that are nylock or patch lock?
probably. Yeah, I think I
I'd probably
specific.
just do that.
Okay.
Well, then that gets rid of the point of no tools.
Yeah. No, you can still if it's a like a patched wing nut, you can still take it off with your hand. It's just not gonna loosen on its own.
Yeah, I guess that'd be ideal because it would be positive locking at that point.
Lock nut that doesn't lock when you unbolt your hand.
Yeah.
Well, if like nylocks are not locked in that sense. It's just really high friction.
Yeah, but you can't loosen it with your hand.
But like the wing nuts have like a thing to grip it, so it's meant for vibration, not for stopping.
Oh yeah, for random, not
Are these bolts for the lid of the enclosure or for mounting it to the car?
mounting it to the car. Yeah, I mean the next. I'm literally gonna have an image that basically shows all of this. The last part is just I had to drill out the holes myself into the firewall to mount the enclosure, which is prone to error. It was a little difficult to do it, and I'm not sure how to do this entirely. I'm talking about this last requirement here, because the idea is you want it to be level with the chassis, and so once you drill the holes and then remove like the firewall, then you can't guarantee that the holes you drilled are level with the chassis. So ideally, you drill the holes and never remove the firewall. But I'm not sure if that's possible. Yeah, we did. We tend to.
Why does moving the firewall?
Well, then you just can't guarantee that the enclosure is level with with respect to the chassis. So your axes will be skewed for your accelerometer or your IMU in general. I guess you could just say, well, make sure that your tolerances are good enough, right? So that it remains level close enough, right? It doesn't have to be perfectly level, but close enough so that you're not like 5 degrees or 10 degrees off.
Can it not like recalibrate the axes?
Yeah, so I could recalibrate the axes, but then I'd have to recalibrate the axes every time.
I mean, that seems more
Easier?
achievable than like having very accurately located firewall, considering how firewall is constructed.
Okay. But that's a fair point. I'll write that down actually.
We've got it in the notes here.
Yeah, okay. That's not what I wanted. Okay. So yeah, this is the actual system. So these are the wing nuts there. Not gonna do heat inserts. I'm threading right into the box. I don't like the heat inserts. I have oversized washers because the firewall it was caving in without them. I don't know if I need them on both sides though, because the other side is aluminum. But that's what I have right now. Yeah.
I know last year the USB thing, the mini USB.
Mm-hmm.
It looks like you've considered that in the new design. Trying to route those, but like, is there a proper length or like an inch long USB that you could use that will?
It would be nice to have one that doesn't have such a large protective layer, because that layer is only like if you're using it a lot, but in this case, we're just going to plug it in and we won't touch it. So it doesn't need to be so robust.
One thing to note is the location of the micro USB connectors themselves have been changed on nav.
Those aren't the locations?
Those are the new locations.
Yeah.
But primarily, the reason you had so many issues is because those two, first of all, it was only one micro USB,
right?
But it was also on, you see where next to that bolt, it was roughly around the bottom.
Yeah,
right
it was
bolt.
pointing this same direction.
That was the issue.
Is that connector 1 at the bottom and connector 2 at the right?
Yeah.
So
it's still gonna have to do a weird bend to get to that one at the bottom.
The bend will be a lot better, because before it had to do a weird S, really snaky. There was like no
it was
space.
remarkable that it fit.
This time we can plug it in from the front, and even though it has to do a bend, the bend will be something
manageable.
That's actually
It's still gonna be an annoying bend.
Yeah, I am saying here I would need to check just to make sure, because I did make it longer here. It used to be 0.8 inches, but now it's like 1.2 to the wall, and then 1 inch to here. So it has more room.
Yes. And that thing can't move, can it?
No, nothing here to
There's
move.
no. You can't like put that gray connector to the bottom
This
and
one?
the micro USB to the top.
Well, the reason why I did this way is because this is the smallest that you can make it. So I mean, I could swap around some things and make so that there's definitely enough room. It would just be a bigger enclosure.
I mean, once this is all routed, it never needs to come out again.
Yeah.
Which I know you were talking about. So
I would really like it if this thing is closed and then you never have to open it.
it genuinely does. Like other than the antenna, the USBs, because all this is a USB pass through, and you can take the enclosure out of the car.
Yeah.
So literally, you can plug in USBs from those external connectors all the time. So the inner USB wiring actually never has to.
I thought we had an issue this Saturday with flashing TV.
That's not. That's not from these two USB ports. That's from the debug headers up there, and we're talking about the wire. I was talking about the wires inside of the enclosure, which.
Yeah, ideally, the problems that we're having is just because once we can wirelessly flash, then I mean there should be no issues.
All right, let's move on.
Wait,
Yeah.
second, I have some questions. Are you machining this enclosure because that doesn't look like sheet metal?
Yeah, this is not sheet metal, so it would have to, if you're making it out of metal, it'd be machined. It'd be like a drivetrain project to learn machining. I thought it went really well last year that way.
Is there a way to have these connectors on the same side, even if it's slightly bigger? Because
Like all three of them?
or yeah, or like keep it to two sides. Because from a routing perspective, you'd have to get to the card from like left, right, and top or bottom. But I'm assuming that's going to be on the top.
Yeah, I mean, I that basically I just have the three on this side and then the one on the other. Yeah, I mean, it would be quite bigger. But yeah, I could do that.
Could you put some on the clear top?
I want to stay away from doing that.
Like it's the enclosures are mostly air, so even if it's larger by volume, it's usually not that bad, and generally just having more access for electronics is better.
I mean, this one it'll be like above the battery now. 'Cause I don't see it as being an issue unless there's like something like if there's something next to the enclosure, then we can have an issue. Right. So if there's something above the nav box right here, then we'll have a problem. If there's something to the other side, then we'll have a problem. But I don't know if there's anything that high up on the firewall.
No, but we should look at it in CAD after this.
Okay. Yeah, I mean, I don't think it'll be an issue.
Let's talk about the controls.
Yeah. Yeah, so I did do the same thing for like force sensing, but I don't think that's important to go over.
This is just a testing thing, right? You're not gonna have the load cell on the competition card.
Not on competition. So we can just go like where I want to put things. So I've marked the chassis tubes that I want to have tabs for the load transmitter, which is basically just a calibration thing for the sensors. And then yeah, nav goes there, and then this is what I'm talking about. Having this particular piece, whoops, this antenna like there instead of there.
Okay, so that one in the middle behind the road, that's the shoulder harness mounting bar. There is a new rule about what you can put on that. I don't remember exactly what it says.
On this one?
No, the one
The
below.
one below.
Oh, you're talking about that. Oh,
Yeah.
well, it's going to be on the not on the tube, but on the wall, the firewall.
On the firewall.
Yeah, it will be on the firewall.
Did you say you wanted it by the center of gravity?
Yeah. So this will fulfill XY center of gravity, but it won't fulfill Z.
And that's okay.
Yeah, that's what I was talking about. Because yaw rate is the largest one, and pitch and roll are pretty small. It's okay to move
cool.
Z axis. Yeah. So this is the placement. And then wheel speeds. I kind of again, this is not something that's super important. The one thing that I was trying to impress here is that right, where I have your robust, strong wheel speed designs the principal innovation that are driving my requirements. We have designs that give good estimates, but they are liable to break either mechanically or, in the case of the motor controllers, electrically. So something that is not doing that is what I'm trying to get at here. And then I'm just talking about the fact that comparators are in fact improving the estimate. Bottom is without, bottom, top is with. Yeah, no, we don't have a CAD for this yet. I believe this is like a drivetrain thing.
Yep.
Yeah, generally we're just going to do a side mount here where it's pointing into instead of above.
So you're using a Hall effect.
Yeah.
From the rotor, brake rotor. Yeah.
Yes. So now we get to the actual controller requirements. Yes. All right. So when it comes to the requirement of maximizing available traction, there's only two functions that actually have to exist for this. The first one is the throttle map. This casts our system into a state that is controllable, because without this function, I do not know the mapping between a torque and a motor command that I'm sending to the motor. So that's all this function is achieving here. So VB is battery voltage, omega is your motor shaft angular velocity, and then R is what I call the power ratio. It's just a ratio between the power that you want to consume right now and the maximum power that you could consume right now. So this is exactly the parameter that is output from my controller. I'm telling it, okay, I want 50% of the power that is available. And then K is the actual number that you're sending to your motor controller. Yeah. So in terms of the actual function that calculates this power ratio, all I've done is specify the maximum number of parameters that could be used to calculate this. Less could be used, and in fact probably will be used, but yeah, I've just said this is the maximum. And these other ones, I've already gone through like the rule of thumb in the specifications before about how 5 to 10 times faster than human reaction. And in this case, the way I'm going to guarantee that the calculation is fast enough is that the only severe computation is going to be the simplex optimization algorithm. I will not be doing any complex state estimation. At best, it will be something really simple. Yes?
So something that I don't remember if it was this year's comp or last year's comp, but I remember one of the design papers had like questions about our justification for using a 15 millisecond.
Yeah, this is that requirement. This is that
Okay.
Justification.
Okay.
Now, I furthered that to constrain it even more about with this whole idea of applying the control action within 10% of receiving new data. So this would be basically saying that I'm able to calculate. So if this is saying I need to provide a new control action every 20 milliseconds, what I'm saying is I need to calculate that every 2 milliseconds. And that's just fulfilling the definition of real time. So yeah, to do that, the only thing is simplex, and simplex takes about, I'm estimating it's going to take 2 milliseconds on the new hardware, so there's no more room to do anything more complex. Now, filtering, this sort of reasonable effort for reducing noise, disturbance, and accuracy, I am stipulating here that filtering methods that induce a time delay on a signal shall never be done in software, and hardware use shall only be used if sensor accuracy increases. So what is not permissible is if you're just trying to make the signal smoother. If you're just trying to make the signal smoother, you are not allowed to use hardware filtering or software filtering. Yes?
So does this apply to the throttle pedal as well?
So I had a certain set of signals in mind for this, and it was meant to be applied for yaw rate, velocity, wheel speeds, basically the ones that are specifically meant for my domain.
Yeah, because the throttle pedal currently does exactly that. So I want to make sure.
Yeah, so it's not estimating a state; it's estimating a because the throttle is different because it's a user-driven input, and that noise you can very concretely say cannot be from the driver because no one flicks their foot that fast. You know that's not from the driver. So it's permissible to start doing stuff like smoothing out the signal because you actually are increasing, in this case, you are increasing sensor accuracy. That's the idea. So yeah, that if part here is important. In the case of the other signals, it's entirely possible you're not. Yes.
So is this a requirement for you or for the team?
This is for me. So
And there's no filtering on the current board, is there? Hardware?
which one?
Yeah.
Yeah. Some of the BMI has hardware filtering.
So there's filtering.
Yeah,
But that
I might use that.
increases sensor accuracy.
If it does, I will use it.
Okay.
Yeah.
Okay, cool. Because I'm saying like once the board's designed, then like
There's
so it's done. There's not any more hardware.
there for the sensors. There's a thing that you can put that sets the hardware filtering. Yeah, so you can make it so that it basically does no filtering or does a bit more.
I don't remember if we're using the filtered output already.
I don't know either, but it's something that I want to investigate because there is surely an optimal. Yeah.
In terms of PCB design, this PCB is already
Good to go.
Tested?
Yeah, it's already good to go.
Wait, we did? I thought we did test it on Saturday. Or was that a different?
That's like, I'm talking about the one in the slideshows.
The F7. Giga micro.
Yeah, the last one is just talking about if you do want to improve sensor accuracy, my prescribed way is adding more information. So if you want to improve sensor accuracy, you should combine multiple sources of information. The only one that this is really relevant to is estimating yaw rate because we have GPS heading and BMI angular acceleration or velocity. So at most of that will be the only sensor fusion that happens, and that is really simple.
Do you not use wheel speed differentials for yard?
No, there was a reason why we didn't.
Slip.
Yeah.
Okay. That's fine.
All right, so this is where all the rules questions are. There are a couple that I enforce that should also be enforced by electronics. So yeah, supplying power in reverse and then cannot regenerate if you're going slow. I do this or will do this in the future. In the case of regen, it's just not applicable at the moment. But yeah, this should also be enforced by electronics. I do not promise anything.
But we need to do a throttle map for those questions.
Yeah. So there's a couple of rules questions here. Throttle map, I want to ask if it's permissible. I expect that it will be because I think I can argue that it's not even a control algorithm.
We should get that in.
And then so I'm not actually going to put regen on the car this year. I'm just looking at the requirements and seeing if we could in future years. And so these rules don't indicate whether or not you can have a separate control for regen, but it seems to prescribe using the actual brake pedal travel for that purpose. That's what it says right here without actuating. Yeah, you can do pretty much the whole range. So I mean that might indicate
like the when you're regen, the sensor you would use for regen is position based, but the brake pedal is force based, so the pedal doesn't actually move basically at all when you're braking, even if you're hard braking.
Yeah, that makes sense actually.
So basically, but whereas regen is incremental, you can choose to do more torque.
Brake pedal does not.
Yeah, I know.
So
One thing that might
Unless you use like a load cell to reach it.
That'd be wild.
I mean, that's what a bunch of sim racing pedals do.
Or
They use load cells.
or you just do a transducer on the actual brake line. Yeah, I think that's all. Oh, I guess there's one that talks about an ESF, and it says the word control and interactive system. I don't know what this word control means in this context.
Have you opened the ESF?
No,
There's
it probably is.
there's a couple sections in there that make us describe like the path of torque request to
Uh-huh.
the motor. So in our case, for example, we go from dashboard, throttle pedal to dashboard, and then we had it listed as then to the torque vector in PCB, then to PDU, then to the motor controllers. So there's a couple. There might be a couple things you have to fill out in terms of controls there. But
Is it just like the electrical path, or do you have to say something a little more about what I'm doing?
it's the electrical path mainly, but I'd recommend checking. We can talk about this later, but just check ESF.
Okay, check
I
ESF.
don't know what they're adding this week. Maybe school.
Okay. And then this is like the life cycle. Not super important. First one, I'm just stipulating exactly what FMEA looks like. I'm talking about alternative modes of control if I can't do torque vectoring. So here I'm saying one potential way is just to go around the actual torque vectoring function, determine this power ratio, like literally just as being equal to the throttle. And then if it's really bad, I can't even do like the throttle map. Then I'm just referring to what we normally do, which is throttle is what we send directly to the motor controllers. Those are the only two modes that could be used. There's nothing else. I'm not going to do some sort of intermediate torque vectoring kind of sort of. It's either it's fully or not. And the other stuff is about the actual code. I've done a lot of work to try and make it as easy as possible to modify, debug, and tune it. One notable thing here is tuning. I do want a way to do that, and I think that's already going to be done. The only addendum here is that I do want a switch. I'm not sure if I put this here. I don't think I did. Basically, a switch that can basically force the car to use one of these alternative modes. I think that'd be good. Yes?
So what's the difference between R and K again?
R is like power ratio. That's exactly what I want. It's a ratio between like the power I want the motors to be pulling versus the maximum that they could pull at that instant. And then K is the actual number we send to the motors.
Can the controller like know if the sensor like it's getting garbage values from the sensor and shouldn't use that?
I'm trying. That's what FMA is really going to be about, basically, just determining whether those values can be used. Yes.
For the switch on dashboard,
Yes.
would it just be? Does it need to be a physical switch, or can it just be something that we do through the screen?
I guess it doesn't really matter. If you don't have enough space for a switch, then it's fine not to have a software switch.
I think a software switch would be the way to go.
Okay.
Like right now, the current plan is to have a rotary for baseline and then buttons to just change stuff on that. So this
Yeah.
would just be like control stage
Yeah.
on off.
I like a little.
I mean, I like the idea of a switch.
The problem is we already have.
We'll get to you.
Switches on dashboard. We have.
I don't think we should have
DAC switch on dashboard, and dashboard is already ordered.
Oh, you can't have a new. Well, no.
You mean switches like in excess of the 3 buttons that we talked about?
What?
But
Yeah,
we talked
in
about
excess
it.
of the 3 buttons.
Okay, we'll talk about it.
You had a question?
I was just with regard to this kind of failure state, like should
Well, this is what
TPS not come along as intended, defaulting back to simpler functions. Does EDIF play a role in that?
No. EDIF is a kind of sort of torque vectoring and I explicitly said that we're not going to do a kind of sort of torque vectoring. It's either going to be torque vectoring or not. And in fact, if torque vectoring doesn't work, EDIF wouldn't work either. You wouldn't be able to do either. So, well, maybe you could, but it would. I mean,
Wait, so if torque vectoring couldn't work, would then, like, if EDIF can't work without, like, if torque vectoring and EDIF need the same parameters and one of those parameters fails, then can you even do R is equal to 1 1t? Or would it just go straight to K?
So I guess if you were to have an EDIF that is purely based on wheel speeds, then there's an instance where torque vectoring wouldn't work, but EDIF would, right? Because the only reason why you couldn't do this one is if voltage and wheel speed, one of those two goes out, and voltage or wheel speed would be pretty bad going out, especially voltage, right? If something like that goes off, then we're not driving probably, anyways. Yeah, I think that's it for this slide. And then this the actual design, right? So we get data from DAC, and this goes into state machine, and the whole idea here is to determine if torque vectoring is permissible. Otherwise, you do equal K, right? That's the idea. And then next, you actually take the signals which you've determined to be okay, and then you provide an estimate for the chassis speed and chassis yaw rate for torque vectoring if you have determined that it's appropriate. And then you do the function that you have determined is okay. Ideally, it's torque vectoring. Yes?
Really quick, I see the if wheel speed or voltage cannot be used section. When you say wheel speed, this is a combination of the 22 or the 23 test that just happened and the and future. But what are you using for wheel speed right now?
GPS velocity.
Okay.
It has appeared to be close enough for verification purposes. Yeah. So torque vectoring, all it does is it computes this power ratio that I've mentioned before. But the motor controller does not talk in power ratios. It talks in this arbitrary, basically, number K. I cannot really ascertain a meaning for this number other than it's like a velocity set point. The only thing that you can guarantee when you set a K value is that your steady state velocity will be some number. What it does actually is anyone's game. So that means first I check here for torque vectoring. There's a case where the output is wrong even when all the inputs are right. So I have to check that, and there might be some other things that go on that I need to check there. And once I've done that check, then I do the actual throttle map, which is computing the K that I need to operate at the power ratio that I want. Yes.
Is this whole thing happening every cycle?
Yeah.
Determining if. Okay.
That's the intention. This should be quite lightweight. It won't be that heavy.
Okay. Just wondering, I'm not sure how stringent it will be on setting, saying torque vectoring good, and if it's not clearly defined, maybe it's keeps flickering back between torque.
Oh yeah, you're right. So adding appropriate hysteresis is very important for a control system with switches, because you don't want the switches to just start going crazy and flipping.
Yeah.
Yeah, I agree with that. That's actually important to know. I did not put that here, but you're gonna note that adding appropriate hysteresis.
Yep.
Yeah. Oh. I don't like that it says present from the beginning. Is there another button? Okay.
And regen is its own control system as well.
The idea is right now it'll be its own control system. But again, it won't be implemented this year. We're just looking into it. We will, no. Unless something drastically goes right. that I can basically show like basically a throttle map for regen. If I can do that, and show, yeah, if I can show a throttle map for regen, then we can go and talk about doing it. Because then at that point, I can show you that I can tell you exactly how much current will be going to the battery if we do regen, and that's, I mean, that's the most important thing. So now I'm just going over all the functions I just listed in high detail. So for the state machine, I'm basically I have it's a very short list of things that could go wrong. And the idea is I'm checking all of these for all signals that are appropriate. Some of these, I mean, they're handled, as I say here, they're handled by electronics. So any serious fault that would still break my control system would break the car. That's the battery over current, under voltage, over temperature conditions. So the principal ones I'm checking to see whether or not I can actually execute torque vectoring is just that there's a recent and in range estimate for all sensors, and then that basically that the functions are executing on time. When I say value is probable, I guess I have the definitions down here, right? So value R is probable if and only if the function that produced the value consists of recent and in-range inputs and outputs. So it's a very simple check. You're just doing it for all signals very strenuously.
So if I understand your third bullet point there correctly, what you're trying to do with TD is prevent a fault from happening, but if it does happen, then that's electronics something to handle. Like
So
if you
for
see
the
the battery getting too hot, then you're going to do it wrong.
yeah, I'll do it so that the car doesn't go crazy.
One
But
thing I'd say is a lot of this stuff is already done by electrical. Like for example, the battery overcurrent under voltage, that's actually done by the Orion itself. And the Orion cuts us off, we're cut off. And things like the motor over temperature or motor controller over temperature is also done through PDU faults. That'll cut the car off, you can't drive.
yeah,
Yeah.
so what I'm saying here is TVS may attempt to stop instability conditions. This is basically looking
Yeah,
in
I
and
see.
saying, it looks like we're about to hit one of these conditions. We're going to stop that. So now, like, there shouldn't ever be battery overcurrent. Yeah, so, well, for battery overcurrent, there's like the idea that the BMS discharge current limit might decrease over time because the voltage decreases. And I will basically enforce whatever that discharge limit is. I'll enforce it so it doesn't happen.
You should be able to additionally, I don't know if this is important to you, but we do send the discharge current limit that the Orion has set.
Yeah, that's what I'm saying. I'm going to be using that number. I could also do like fancy things with under voltage. Like if you never want to be under 200 volts, I could guarantee that by limiting the current. And then likewise for motor and motor controller over temperature. If they're starting to get hot, I just have like this default mapping that says decrease by X amount until the command is 0 at the over temperature condition. Right. So it wouldn't be possible to drive the car if you're at that temperature anyways. And then this is like the actual logic going between states. So okay, so this is where I actually say that these conditions of equal torque mode are just gonna be set by a switch. Is the idea. So this wouldn't naturally happen in the code. This would be something that you're telling the code to do generally. Otherwise, the idea is that you have a sensor malfunction situation that's causing you to go to equal torque mode. So this is just a wall of text going into detail about how I will estimate chassis speed and chassis yaw rate. There's not much to comment here. You're not going to be really changing altitude, so taking the north and east components is fine. And then, yeah, you can fuse heading and angular velocity to get yaw rate. And the one thing to note here is that yaw rate is probably the weakest link for estimate, and adding another antenna would probably have the most impact on control system performance from a perspective of estimating states. We don't have a second antenna for this year. It's already finalized, but in future years, it might be something worth looking into because it would, compared to any other way to improve, this one would definitely be the most cost effective. Yes?
You use this BMI,
Yes.
and then you're saying that
BMI 88 has been used for a little while.
one of the two sensors will prove to be better. Do
Probably.
you know which one already?
I expect it to be the heading from the GPS because it's no
used-
bias.
You've used it before? or
No,
not?
because
This is new component.
yeah, I guess I haven't. Well, so I haven't actually looked into detail about the quality of either of these sensors. I expect the GPS to be better simply because it doesn't have a drift. It won't drift because it's an absolute reference, whereas the BMI will drift over time. So I mean, eventually you can say for sure that the GPS will be better. But if we're only driving for 20 minutes, and we just calibrate the IMU, it could be better for that duration, right?
Okay.
That's the idea.
But you've tested one or both of these?
We have data for the BMI. Yeah.
So you know it drifts.
It
Or it says it
does, but like it does because of the nature of the sensor.
I'm just wondering because
But I haven't looked at like having a reference and the sensor value. That's what I need. That's why I've been working on with Ethan to get that reference, so that I can tell you how good it is.
okay.
Yeah.
Sounds good.
And now now we're going really into this is like actually what torque vector does. So first, I'm just determining the maximum allowed power. That's what it does. It doesn't set a power target. It sets a maximum allowed. And this is literally just what the pedal says. So if you're at 50% on the pedal, then you're saying maximum power allowed is 50%. That's how I fulfill the rules for that. Then I have I'm planning on having a map that determines what I want the yaw rate to be, and then I convert this error between actual yaw rate and the desired yaw rate into just a difference in torque, so difference in power and difference in torque are equivalent in this control scheme. But yeah, it is a difference. So I do describe that difference. That is what I want the difference to be, and then I formulate the actual optimization problem and solve it. So the first step here is setting a power limit. So there's individual motor limits. Right now, I just have those to be constant. In the future, if you want to do a four-wheel drive with normal force things, then this is where you would have variable individual limits, right? Because then you're saying, well, you're losing out one of the wheels. You want to clamp down that wheel. And then the other one is determining the overall power limit. And this is where I'm talking about the temperature over temperature conditions, over current conditions. So I have like a discharge current limit. I convert the temperature of the motor controller to like a current limit. And I do the same thing for the motor. And then I just take the minimum current from all those. And usually it should be just the throttle that is selected. But in the case of, we're operating in a really dangerous condition, I will choose the lower limit. And this calculates parameter B, which is you'll see it's just part of the inequality setting the maximum power allowed. Next thing is the yaw rate map. So this is the map that I want to obtain from the vehicle. Yeah, at the beginning, you can predict this linear part of the map basically from the geometry. But as you go faster, then tires and other things start playing a role, and then you have this really nonlinear relationship. So this map can be obtained via open loop testing. This is what I have shown here. You can also do this by driving the car until it reaches steady state. You set the pedal position, you set the steering angle position, and then you just drive it until the yaw rate stops changing. So once you have that, I forgot to do this slide. So this is the one slide I did not do, but I mean, it's literally just a peak controller. I have a desired yaw rate. I have the actual yaw rate from the estimate, and then that's proportional to your delta that you need.
I gotta head out.
Yeah. They almost finished.
So, like,
Yes.
you had a PI controller before, right?
Yeah.
So why are you dropping the I?
So to appropriately have the I component requires this horrific. Okay, so I don't have MATLAB open, so I can't show you that. But it required a lot of additional things. So the first thing I needed was a saturation to make sure that your integrator stops once you reach the maximum control action possible. And then I needed to add a hysteresis to that because you want to stop the integrator, but then you don't want it to like start doing a twiddly thing because that's a switch basically. When you add that saturation, you're adding a switch, and so you need a hysteresis for that. And then, yeah, that itself was complicated enough. I did figure it out, but it was complicated enough that, I'm just asking myself, is it necessary? And I don't think it is, because I don't think it, basically because of the way the yaw rate map is set. The yaw rate map is the yaw rate you'll get at steady state. So I already know that if you're in that steering angle position long enough, you're gonna reach steady state without your I component, because you're gonna reach that steady state without any control action being applied, without any delta being applied. So you don't actually need the I component to reach zero error. Yeah, that's the most simplest way to do it, to say it, that last sentence.
So, ideally, the best way to drive the car with torque vectoring on is literally to floor it everywhere and have torque vectoring do its job.
No.
A hairpin would disagree with that.
A hairpin would disagree with that. However, it will apply, like if you're spinning out, it will apply counter steer. So flooring it would be safer than normal. That's all I can guarantee.
So, okay. Well, it couldn't apply counter steer, it could only slow down the outboard wheel. That's all it can do, because you can't boost the inboard wheel. By rules, because you can't apply more torque than this commander.
Total torque.
That's what the rule is, total torque?
It says total torque, yeah,
Okay.
specifically. Now, yeah, this is probably another rules question about the exact way that I can do this, because I can think of a couple ways that you can do it, and some of them might violate rules, some of them might not. Yeah. So there's at least 3 rules questions that should be asked. Yeah, this is the actual optimization statement. So your t vector here is your actual decision variable. I have generalized it to be 4, but right now it's just 2 decisions, right? Your power ratio for your left and right, and then C. This is unnecessary for right now, but in the case of traction control, what I'd be doing is I'd be modifying these weights to prefer one side or the other, or front over the rear. So I want to maximize the total power consumption, which is saying I want to maximize the amount of torque that's being applied to the ground. And then this b parameter, as I said, was the maximum allowed. So that's just nothing but the sum of your decision variables, right? And it must be less than this number b. And then this delta t is calculated from this dt controller, right? It's just calculating the difference between the torques must be that. And so this k is the moment arm from the center of gravity, right? So I have here, right? So this some number, some distance from the center of gravity. One of them is positive, one of them is negative, right? Because it's doing a moment. So that's how I do that dt right there. This is generalizable to 4 wheels when you do it this particular way.
Okay.
And then then you're enforcing individual torques. Again, this is really only relevant for like a normal force 4-wheel drive controller. It's just I've generalized it so that it will work that way. Right now, these bounds are just constant. Yeah. The funny thing to note here, what the actual simplex optimization, when you have a linear cost function like this, it's just a logical solver. Yeah, I mean, you could solve a much simpler problem without using the simplex algorithm. Basically, solve this problem without the simplex algorithm, and it'll be faster. However, if you want to do this with 4-wheel drive, this will become monstrously more difficult. And so using this simplex algorithm is a simple way to definitely get the right answer, and it is fast enough.
So why is torque, why is the upper bound for torque constant and not a function of traction?
So the way my controller, I don't have enough available variables, basically. So my yaw rate is already stipulating a relationship for my decision variables here. And so I want to guarantee a certain pedal, like a certain throttle, and I want to guarantee a certain delta. That's 2 motors, 2 unknowns, basically. So it's insufficient to have another constraint. The idea is I've designed this yaw rate map so that it gets you closer to maximizing traction.
Okay. So the upper bound is really just like a lookup table then?
Upper bound is just, it's a constant. What do you mean?
Wait. So you're saying you're making a yaw rate map to figure out how much torque you can apply in given conditions?
I'm using my yaw rate to determine the delta that should be between each tire.
Okay.
The idea is that this delta has the special property of increasing traction.
Gotcha.
Yeah, it has that property. Now, if you have 4-wheel drive, this constraint is insufficient. You have 2 more decisions that you can make, and so you can add another constraint so that you're getting even closer to maximizing your traction. So, yeah, this is very technical. This is not super important. But a couple of things here. I haven't really looking into like giving a guess for this algorithm. If you give it a good enough guess, it will solve faster, right? And then, yeah, there's like this constraint violation that I'm allowing for my delta that doesn't have to be there. You can calculate whether or not you're going to be violating constraints ahead of time, and that's probably faster to do. So, and then you just adjust for that constraint violation in some way. And then this output here, like I've calculated the power ratio here, and all of this is that second state machine part that are just checking whether or not this solution is okay. Yeah, and this is going into actual depth. Like, there's a bunch of different things that could happen when you run the optimization. You could find that it's infeasible. You could run too many iterations of the optimization and not find a local minimum. You could find that it's unbounded, or you can find that it's an optimal solution. And my claim here is that the only instance where I can take the solution is if the output is 3 optimal solution. The other ones should not happen. Too many iterations. Like there should be a local minimum somewhere all the time. If there isn't and it can't find it, then there's something actually wrong.
So how does the control algorithm handle receiving a 1 or 2?
I revert to one of the simple forms. Yeah. So
Is that a permanent reversion? So like the first time you get this, it's like we're going back.
only when it happens. Only if it isn't 3.
So it would be switching between.
Yeah, this is another switch.
Okay.
In practice, this should never happen because, like it might happen if you lose traction. If the car is actually spinning, then it might have a hard time finding a solution because it's not possible. Right. So yeah, if it's not possible to find an optimum because everything is bad, but in that case it's trivial to say equal torque or not equal torque. It doesn't matter. You've lost traction and you should just stop driving. Yeah. Oh, my image got moved. Who did that? It's probably me. That looks closer to right. So this is the actual throttle map part. You have your power ratio, your battery voltage, and your angular velocity of your motor shaft. I have a map here that basically says, all right, so given this voltage and omega, this is the largest K, or the smallest K that can be sent to the motor controller that will yield maximum current. And the novel realization here is that this number is not constant. Right? You would expect that this number would always be 100% throttle, right? But it is not. And then likewise, largest number that can be sent to the motor controller that will yield 0 current. This is also not constant. This is also not equal to 0% throttle. So once I find these minimum bounds, the true minimum bounds, I do a simple linear interpolation using this power ratio to find the actual K.
So you're saying K-min and K-max are not constant?
Yeah.
So how do you find out what K-min and K-max are at a given point?
So what I do is, so let's see, so for the min K, this is a nice question. So this entire table is obtained from Plettenberg data and is probably good to go without any further modification. What this table is that given, they give you no load RPM at different voltages, right? So that's like one of these curves is the no load RPM at the volt at or how do I map this? So they give you a number for each one of these, and it like the curve will like follow this sort of path, right? As or how it'll follow some sort of path. But yeah, you can plot that for all the, you can do one curve of the actual Plettenberg data, no load at this voltage, and K equals 100% throttle, because they only give you the no load RPM for a given voltage at 1 throttle, which is 100% throttle. So you can plot 100% throttle, no load RPM for 1 voltage. And then you can scale that one curve to all your throttles, because basically what the engineer said is that if you have 50% throttle at 300 volts, this is equivalent to 100% throttle at 150 volts, right? So you can do that scaling. So given that one set of data, I scaled it to all the different throttle positions, and this is the curve that you get basically. And then the other curve which is the maximum K. Yeah, this partially comes from Plettenberg data. So what the data that I got from Plettenberg was this ridge right here. The first point at which K equals 1 is in fact the command that you have to send to get maximum current. But I don't have this curve below that. And so this is what we get. I had to do this from testing data, where we did the set throttle positions, and at some point, the like 50% throttle deviated from the common curve that all the throttles set, and so using that point where it starts deviating, that gives you a point on this graph. And I end up having a single curve. Again, we only had a single curve because we only tested at basically 1 voltage. But I scaled that curve as well to work with all different voltages, just as a first approximation. And it should be close anyhow. And that's how I got the entire surface. And then here I do a difference between these curves, because these curves look almost identical. And as it turns out, the difference between maximum and no power is no more than 30% of pedal range. It is never more than 30%.
Without the map.
Yeah.
Does that like correlate to what driver said? The default one?
So the thing is that these motors are not super powerful.
Right.
And so when you give it maximum, it doesn't intuitively feel that way. I think that's what's happening. That's what the idea of, it feels delayed, because the torque map is like the amount of torque that you get doubles over the course of the RPM range. It's something ridiculous like that. So it just feels like there's a huge delay.
Isn't that partially because we're hitting the current limit?
No.
Oh.
No. So I mean, if you give 100% throttle, your current will go like that.
Yeah.
It won't hit. I mean, you'll hit phase limits. Is that right?
Yeah.
Like the actual phase current might be like maximum, but the current it pulls from the motor controller isn't.
But like,
Interesting.
There's a setting in the motor controller for how much current, both DC and AC, it should receive and send. And
Well,
I believe
then-
it just cuts throttle if you hit that limit. I could be wrong. I don't know what the exact figure is.
If there's a setting for both DC and AC, then yeah, it would be hitting AC current limit.
There is a setting for both.
Okay, then yes.
Currently, the DC and AC current, it's actually called phase current and regular
Yeah.
current.
The phase current.
But those are currently both set to, I believe, 55 amps. Yeah, 55 amps.
Why can't we increase the phase current?
We can.
That would probably be beneficial, actually. That would help with startup. I would
Because,
expect it.
Like the real constraint on current limit is the back fuse, right?
Yeah,
Which is a DC current limit.
I can double check the Plettenberg documentation. Let me do that real quick.
Also, I'm not saying you should do this, but
Oh no.
I don't even know if this is possible. But one way to get around a lower back fuse could be to dynamically change the current limits.
So the way you would have to do it is you'd set the motor controller to be at 70, but my map has it so that it caps out at the appropriate current, because you can't really dynamically change the motor controller.
I think you can. It's like the command structure is the same as what you would send to change the throttle. And whether it behaves properly when you change the current limit while it's pulling current, I don't know about that.
I would say that using a map, as I say, would be cleaner.
Yeah, like I'm not saying you should do that.
Well, so actually, this would also be a performance increase, because, well, specifically because of how Plettenberg did it, how they enforce the current limit. It's really annoying. So like, if this is your if you just do maximum throttle and then this is like your current, right? It drops off. They like scale it. So like.
So like there's some like protection.
Yeah, they scale it this way. It would have been nice if they did it like that, right?
Yeah.
but yeah, you're literally losing all that. It's annoying. It makes it easy for my throttle map. So you asked the question about does it matter for current limit? Because they scale it this way, it doesn't.
Okay.
So there's a niceness to having the scale, but yeah, it is performance loss.
Okay.
So yeah, there is a phase/battery amp max that you can set. We can go about maybe adjusting the phase current limit to be above 55 amps per motor controller. I don't know. I'd have to fashion a little more connector, but so that wouldn't be a today thing. That would probably be.
Yeah, I mean this is just
It's
for
a software setting, so
yeah.
it's not critical.
Yeah, that can happen anytime. Just don't forget, right?
The software setting is much better. Sorry, we have to fashion a little harness.
Yeah, I'm saying if we wanted to test it because it's only a software change, you can have it like anything basically. It doesn't even have to be back testing. You would see this, you would just use it.
Yeah, we'd have to apply high voltage to the car.
Yeah, yeah. You need the battery, but you don't need the battery. Well, I mean, questions, you already asked questions. So
Yeah.
I don't really have any more.
Fine. No questions then. Okay. That's all I have. Thank you.
Very
Yeah. I didn't go over everything. I did skip over wheel speed and normal force, but the important thing there was just the pictures. So all the pictures are if you need to reference something, it's just all the pictures.
It's also like really good knowledge